for this session of Wired seminars. Um, Today, Irtaza is going to do a presentation. Irtaza is a master student at the Department of Electrical and Software Engineering at the University of Calgary under supervision of Dr. Farrokhabadi. And the title of his presentation is Impact of Wildfire Smoke on Distributed PV Performance. After Irtaza's presentation, we will open the floor for the questions and responses. Irtaza, please go ahead. Thank you.
Thank you, Fatma. Hey, everyone. Are you able to see my screen?
Yes.
All right, thank you. Um, Thanks again for the kind introduction. I am Irtaza, and I'm an MSc student at University of Calgary, working with Dr. Mustafa Farrokhabadi. And it is my pleasure today to share my work with you on the impact of wildfire smoke on distributed solar PV performance. I will try to wrap it up in around 45 minutes and then have 15 or so minutes for question and answers. Um, so let's begin. Um, all right, the slide is changing. Perfect. So first of all, I will go through the motivation for this work, then present the data sets that we used, follow it up with methodology results, and talk a little bit about future works. But before I begin, I would like to acknowledge the land on which the University of Calgary is located and where I am a newcomer and am grateful to be able to live, work, and play. The University of Calgary, located in the heart of southern Alberta, both acknowledges and pays tribute to the traditional territories of the peoples of Treaty 7, which include the Blackfoot Confederacy, comprised of the Siksika, the Piikani, and the Kainai First Nations, the Tsuut'ina First Nation, and the Stoney Nakoda, including Chiniki, Bearspaw, and Goodstoney First Nations. The city of Calgary is also home to the Métis Nation within Alberta, including Nose Hill Métis District 5 and Elbow Métis District 6. On these lands, humans and wildfires have coexisted for thousands of years, and today we will be exploring an emergent issue, which is the impact of smoke on solar panels. So this graph shows how wildfire smoke has drastically increased in Calgary. The y-axis shows the number of smoky hours during May to October between 1953 to 2025 during the past decade. Let me see if I get pointer here. So you can see that during the past decade, the average number of smoky hours has increased to more than 10 times compared to what we were seeing in years before that. So it's not uncommon to have several weeks in Calgary which are impacted by wildfire smoke during the summer season. So while the wildfire smokes have increased, the solar PV is also increasing across Alberta, including in Calgary, which is the sunniest metropolitan of Canada. The graph shows the micro generation capacity in Alberta on the left-hand side. And you can trace it in this black line right here. It has exceeded more than 400 megawatt, and about 97% of this micro generation is constituted of distributed solar PV. On the right-hand side, you can see the number of micro generation sites. You can see that there are more than 40,000 sites for microgeneration in Alberta, and more than 99% of these sites are distributed solar PV sites. Within Calgary, there has been an increase of 8 times between 2019 and 2024 in solar PV capacity. So we have increasing wildfires on one hand, and we have increasing solar PV on the other hand. And so this leads us to our motivation that it is obvious that wildfire smoke attenuates solar irradiance, which can result in solar PV losses. So now, how do you quantify it, and why do you want to quantify it? First of all, we have the energy losses. which are closely related with grid reliability and energy security and consumer behavior. And revenue loss is also an important factor when you're calculating payback period of any solar PV system. This is a relatively new field of research, and the studies in Canada are quite limited. There are a few around the world, but each of them have their own limitations. And this is for the first time that we would be using about a decade worth of solar PV and smoke data to find the impact of smoke on solar PV in Canada. Um, to highlight the motivation of this work a little more, I would like to give you two examples. I used to work at an industry which had its own microgrid with a generation capacity of about 40 megawatts. There was a 2 megawatt solar PV system connected to it. Now, this was a process plant and it had a lot of pumps. And the pumps were either driven by electric motors or they were driven by steam-driven turbines. So the plant operators liked to run electric motors because they were more efficient. However, if the solar or if the electricity supply was scarce, for example, if any generator was taken out of service, or maybe the solar PV plant was not available, they would switch to steam turbines, which were less efficient but did not depend on electricity. And so having a clearer idea of how on a smoky day the solar PV output would go down can give them better understanding of how they should operate the plant. Um, for another example can be a homeowner that has rooftop solar PV and an electric vehicle. And they want to charge their electric vehicle, but they want to use the energy from their solar panels rather than more costly energy from the grid. And so with the model that we are going to propose, which estimates that how much energy loss a solar smoke can cause, then a rooftop solar PV owner can estimate whether it is useful to charge their electric vehicle within the smoky hours, or should they wait maybe for nighttime when costs of electricity might be lower. And so given these examples where this model or this study can be deployed, we need a very accessible model. We don't want to have complicated inputs that people like average rooftop solar PV owner or plant operators cannot decipher, extract, or wait for. Basically, our objective here is to develop an accessible model to estimate the impact of smoke on distributed solar PV. Another example, like the question here is, what do you mean by accessible model? And what I mean is a model that uses accessible inputs, which are easily observable or easily measurable. Let's say, for example, clouds. So some studies that it studied the impact of solar PV and the relationship between solar PV and smoke use something called clearness index. And clearness index is wonderful, but the problem is it is available 3 weeks after the end of the month through a NASA atmospheric model. So if you want to make a decision based on smoke right now, you cannot wait for inputs like that. And so a major theme of this work is to make sure that the models we use, the inputs we use are accessible. You can look out, look at the sky, say, okay, this looks clear to me. So how does that impact my panel output? And I'll keep talking about that throughout the presentation. So let's move ahead. Um, these are the variables that we considered in our study. Note that all of these were not part of the final model. We took only the most accessible ones from them. Of course, we need to have solar PV if we are studying the impact of smoke on PV. We had something called the Air Quality Health Index, the particulate matter, aerosol optical depth, satellite and sky images, weather data, including cloud cover, smoke observations, temperature, humidity, and wind speed. So now I will touch on each of these data sets where we got our data from and how it is accessible and how did we use it. So starting off with solar PV. So we had data from 17 sites in Calgary between 2017 and 2025, and from 3 sites in Edmonton between 2024 and 2025. These are the 2 largest cities in Alberta in Western Canada. We had the data we had was at hourly resolution, but there were some issues with this data, including inverter clipping, abrupt changes, and erratic output. Let me show you what these issues really look like. So on the top left corner, you see expected PV output. So on x-axis, you have years. On y-axis, you have normalized PV generation. You can see during the winter months, the PV output is low. It is 0 on some days when there was snow, but it rises towards the middle of the year. And you can see this nice cyclic curve right here. So this is what you would expect the output to look like at a solar PV site over the years. However, this world is not perfect. There were some sites that had unexplicable sudden drop. Maybe it was due to an inverter failure. Maybe there is one portion of solar PV panels that became faulty. We don't know. So what we did is to only use the data which when the system was operating closer to its nominal capacity, and we just cut this portion off. There were some sites where you have no idea what's going on. Sometimes they are producing high PV output, which drops down for a year, goes back up, goes back down, and it keeps on fluctuating. So there's no way that uh, or at least we couldn't find a way with like what to expect, right? You are expecting maybe a higher peak and you get a lower peak and so on and so forth. So we just excluded these sites completely. Another issue that other studies have also ran into is something called inverter clipping. You can see that rather than having nice hills like these, there's a flat top of the solar PV output right here. This happens when the solar PV panels produce DC power that is way too high for the inverter to convert into AC power. And so even if smoke causes reduction in panel output, the power may still be higher than the inverter capacity. So during the months when you see solar PV output being clipped because of inverter, you cannot use those months, the data from those months to analyze the impact of smoke because inverter is the limiting factor there. However, if you look closely, during September and October months, the clipping is no longer a problem because the sun's angle is going down, and so the panels produce less DC power, and so the inverter is no longer a limiting factor. So for these sites, we used data only from the months of September and October, or whichever months were not impacted by inverter clipping. So once we have cleaned the data using all these visualizations, we were left with 14 sites in Calgary and still had data between 2017 to 25, and one site in Edmonton between 2024 and 25. Now this chart shows you like what the size of each site was. So there were 7 sites between 0 to 40 kilowatt. There were two sites for between 40 to 80 kilowatt and so on. The highest site was slightly had a peak production capacity of slightly lower than 1.5 megawatt. Um, so now that we have discussed solar data, let's talk about air quality health index. People in Canada might be more familiar with this than people not from Canada because this is a public health risk indicator that translates ambient pollution to a scale of 1 to 10 plus in Canada. The higher the AQHI number, the closer it is to 10, the more polluted it is. And it is actually calculated using multiple pollutants which are found in wildfire smoke. So we also saw this time series chart and saw that high AQHI, which is shown here in the blue line, and which is uh, also the values for which are on the left axis. When you had high AQHI, the solar PV output was considerably lower. So we thought that, hey, this looks like a good, useful proxy for wildfire smoke. And it is quite accessible. Like in Canada, sometimes if you just open your Google Maps, it would give you a value for AQHI that, hey, be careful, the air quality is not great today. So, but the problem with it is that it is restricted to Canada, and even within Canada, there are slight differences on how AQHI is calculated in Alberta compared to other provinces. And so it's great for Alberta, but then the study would be limited to Alberta. And the another issue is that it saturates at 10 plus. So once the concentration of uh, pollutants is above a certain level, then you can not capture that using the scale, which is fine for health purposes, but maybe not the best for our analysis. So that's air quality health index. Now moving on to uh, PM 2.5, which is particulate matter, which has a diameter of less than 2.5 micrometers. This is a major component of transported wildfire smoke and includes carbon and other organic compounds. These are so since these are small particles, they're more easily transported compared to larger particles and ash from wildfires. So many studies have used PM 2.5 before us as a proxy of wildfire smoke. PM 2.5 is also very accessible because it is monitored for regulatory purposes and also used to measure air quality health index across communities in Canada. Something called the National Air Pollution Surveillance Monitoring Network um, has their monitoring stations all across Canada, and you can access data from them using a portal from Environment Climate Change Canada or even from the Alberta government. We use three stations in Calgary and one station in Edmonton. Finally, just to highlight how accessible this value is, there is a growing network of privately owned sensors called the Purple Air sensors, which show a reasonably good agreement with regulatory sensors and therefore provide a very accessible source of PM 2.5. This figure right here shows you how many Purple Air sensors there are in the city of Calgary, and there are quite a few compared to only three regulatory sensors. So due to its accessibility and transferability across other jurisdictions, we use ground level PM 2.5 concentration as an accessible proxy of smoke for this study. But to compare the PM 2.5 with other proxies, one of which we already discussed, the AQHI, and another one of which we will discuss now, aerosol optical depth, to just kind of see how good each proxy is in capturing the impact of wildfire smoke. So there are three major sources from which you can get of aerosol optical depth, or AOD for short. There are sun photometers, part of aerosol robotic network across um, the province. This map right here shows you there are only three sensors which are active in Alberta right now. And the nearest sensor is more than 150 kilometers from Calgary. So this wasn't really practical for us to use. Another way of obtaining AOD is through satellite images, more specifically the geostationary operational environmental satellite, goes 16 and 17. However, the limitation with these is if there are clouds present, then they do not do a good job. So some studies have used only the days where there were no clouds to measure the AOD using these, um, to use the AOD produced by these satellites, but other studies have found that the AOD data is not easy enough to use, which is obtained from these satellite images. And the third option is model reanalysis, or MERA-2. So MERA-2 stands for Modern Era Retrospective Analysis for Research and Applications version 2. This is atmospheric model, and I believe it's NASA provides data through it, and it, as the name suggests, it's retrospective analysis. So at the end of each month, you have to wait for 2, 3 weeks, and then the data through this model is available. So it's good if you want to look at historical trends, but it's not as useful if you want to estimate the impact of smoke like right now. However, we were just using this to compare the performance of PM 2.5. So for that purpose, it was fine. We can get hourly time average values at a resolution of 0.625 degrees to zero point 0.5 degrees. And the variable from this model that we use is something called the total extinction coefficient at 550 nanometers. This scatter plot right here shows you the agreement, or the relationship between PM 2.5 and aerosol optical depth. The relationship is pretty reasonable, but you can clearly see there are days or hours when you have high AOD but low PM 2.5, and vice versa. And I'll talk more about that when I discuss the results. So now that we have discussed the proxies of smoke and solar PV data, we also used satellite images. These are images taken from NASA's satellites and provided by website called Zoom Earth. So it was useful in counter verifying if, for example, we had a day with high PM 2.5, was it actually smoky or not? So we used this extensively. On top left, these are all sky images from, or satellite images of Calgary during September of 2025. You can see a clear day, you can see a cloudy day. You can see when there are both smoke and clouds. The smoke is a bit light, and then you can see when there's dense smoke. So it was really handy. And then an important metric is clouds. And again, we are looking at the most accessible way of measuring them. So it's kind of, a person who has to use this model just want to look at the sky and say, hey, it's clear. So, go from there. Because there are models which report clouds in different ways, they would tell you, okay, 17.87% of the sky is covered with clouds, but uh, that's someone just trying to observe the sky may not be able to come up with a percentage like that. So what we used is like a simple code, which I will share about where it comes from. And of course, those of you who know way more about meteorology than me would already know about this. But there are two weather reports that are generated typically at airports. One of them is called the surface synoptic observation, which is reported every 3 or 6 hours and include cloud cover and cloud type data. The cloud cover data is on a scale of 0 to 8 octas. 1 octa means that 1/8 or 12.5% of the sky is covered in clouds. 8 octas means that the entire sky is covered in clouds, and 0 octa means everything is clear. So this is relatively, putting a number between 0 to 8 after looking at the sky is reasonable, reasonably accessible. Another way of measuring clouds is through something called the Meteorological Aerodrome Report, or METAR for short. They are also reported hourly, or they are reported hourly at airports rather than every 3 to 6 hours, and they include cloud height and coverage. And so this table summarizes how the clouds are reported in the METAR reports. You can have sky clear, few clouds, scattered clouds, broken clouds, overcast. Each of these correspond to a range of octa values. If, for example, you have, let's say, 6 octas, or 6 out of 8, or 75% of the sky is covered in clouds, then the META report would include something like this, BKN, which would mean there are broken clouds on the sky. And the value that we use now, we are simplifying things here a little bit. So if it says few clouds, it could be 1 octa, it could be 2 octa, it could be anything in between, but we just simply use 2 octas just to keep things simple. However, when we had synoptic observations, which are on a scale of 0 to 8 octas, then we would, like, let's say, you know what, it's easier to go through this flow chart. So we select an hour, we see if a sign-up report exists. Remember, they're only generated every 3 to 6 hours. So if luckily it's an hour when it exists, we assign the value between 0 to 8 from the synoptic report. Um, and move on to the next hour. Let's say the synoptic report does not exist, then we would see the METAR report and assign a value between 0 to 8 based on this table. So for example, the METAR report says there are broken clouds at, let's say, 20,000 feet, then, and there are a few clouds at 8,000 feet, we would just go with broken, 6, and there you go. So that's how we try to keep this accessible and yet rigorous. So the other thing is that not all clouds are the same. Um, Also, clouds can change rapidly. They may or may not obscure the sun. For example, if you look at this image, there are some clouds and there seem to be something in the way of the sun, but the sun could be right here. And so, you have 4 octaves, but doesn't matter if you have 4 octaves or however many octaves you have because the sun is right here. So there are some limitations when you're using uh, values of cloud cover based on hourly observations. Also, there could be something called the cloud edge effect, which can kind of focus light on solar panels and even maybe increase the PV output. But we took average over a large period of time, and so expect that at least some of the effect of cloud is captured through that. The other issue is the type of clouds. Like, clouds can be uh, more reflective or less reflected depending on how much water they carry, and so on and so forth. So there are 27 different types of clouds that are reported in the sign-up reports, and they can exist in different combinations. So we can have total of hundreds of combinations of different mix and match of clouds. And so uh, uh, it can become really tricky to capture the impact of cloud type. These are the different cloud types that existed during the analysis of our window on smoky days only. We had hundreds of data point versus we had like less than 100 of cloud type data available. Because the data of cloud type is so scarce, it is only created every 3 or 6 hours in a synoptic report, typically 6 hours for our data set. So, we did not have a lot of cloud type data, and so we just decided not to use it. Um, so that is again a limitation that you might want to keep in mind when using our model. Also, if you want to use cloud type, then it becomes a little less accessible. I did not know what all the different types of clouds were before I started working on this project, and I don't think I've got them all. So to ensure model accessibility, we just stick with cloud cover and not with cloud type. So finally, we have the weather data sets. All right. So these are quite accessible. The purple ear sensors also measure them, measure temperature and relative humidity, and you just search weather of your city, and all of these variables would be right up there, and so there's not much issue of their accessibility. Another variable we used from weather observations was something called the observation of smoke or haze. ECCC defines that as that if the visibility is reduced below 6 miles due to suspension of small particles in the air, which are produced by combustion, which is basically wildfire smoke, then they would tag an hour as smoky, or like these are basically observations of smoke made by people at weather stations. So it is quite accessible. Like anyone who wants to use the model can see the smoke for themselves. That's kind of the thing. However, there are some nuances in using these values, which I will go into more detail later. To summarize, now we are done with the data part, and we are over half of our time, so I'll try to speed things up. But to summarize the data sets, these are maps of Calgary and Edmonton, which show how solar PV sites, PM 2.5 monitoring stations, and weather stations are spatially distributed. For Calgary, you can see that we are using one weather station right here, which is at Calgary Airport. There are three PM 2.5 measuring stations across the city, and then these yellow squares show the solar PV sites. However, for Edmonton, the airport is way out of the city. I mean, it was about 30 kilometers. And so using temperature, humidity, wind speed from airport may not reflect well in our analysis. So there was an old airport in Edmonton, and we used temperature, humidity, and wind speed data from the whatever of their weather station is left off there, but they do not make any cloud or smoke observations. So those still come from the airport. And so there is a certain uncertainty here that comes because of this spatial mismatch. Now that we have discussed our data, let's start building the model. And for our model, we focused our analysis on smoky days. Now, how do you know which days have been smoky in the past? And people have used different techniques, and we discuss them more in the paper that we will be submitting. But to cut a long story short, we saw the tags of whether an hour was smoky or whether an hour was not tagged as smoky from the airport weather record. And we plotted so we have segregated those hours in two sets, and we plotted the box plot together with the distribution of the of the hours. So when you see this violin plot is thicker, this means that there are more number of points in this slice of PM 2.5 value versus as you see higher values, there are fewer and fewer points with high PM 2.5. So, like ideally, you would expect that for all the points above a certain PM 2.5 threshold, all of them would be smoky, and below a certain threshold, all of them would not be smoky. But you can see there are some points right here up until 174, which can be not tagged as smoky, but which still have high PM 2.5. And then you can have some hours which have low PM 2.5, in fact, as low as 2 microgram per meter cube, but they're still tagged as smoky. So what's going on here? So we reached out to Environment and Climate Change Canada, who said that if an hour is tagged smoky, like all of these guys in red, so you can rest assured that these are smoky. But there is a slight issue when if the visibility is higher than 6 miles, even though you can see the smoke, but the visibility is higher than 6 miles, then an hour would not be tagged as smoky. So they suggested that you uh, use both visibility observations and a PM 2.5 threshold to determine whether a day is smoky or not. So we did just that. And before I move on to that, I also want to acknowledge that there are some limitations when using PM 2.5 threshold because we are measuring ground level PM 2.5, remember? And so the PM 2.5 could be different up in the sky, and we won't know that. So this is a known limitation. Other studies that use this accessible input also suffer from it. This is kind of the cost of accessibility that you have to pay. But even then, we'll see the model performs pretty okay. But I've included a couple of extreme examples when the PM 2.5 was 91 microgram, but the smoke was lighter versus when PM 2.5 was 48 microgram per meter cube and the smoke was considerably more dense. However, we used, however, we still used a PM 2.5 threshold to capture whether a day was smoky or not. What we did is split our hours into bins with PM 2.5 concentration of 5 microgram per meter cube. So let's say, for example, I put all my I trace all my hours that have between 460 and 465 microgram per meter cube PM 2.5 concentration and see whether they were what is the probability that they were tagged as smoky. So, I divide the number of smoky hour in this bin divided by the total number of hours in this bin. And so in this particular case, all the hours in this bin were smoky. So we had a probability of 100%. But let's see here, if the PM 2.5 concentration is between 15 and 20, then only about 20% of those hours have a smoky tag. So, you see this dip right here because the number of hours was really low here between 125 to 130. Right here, you see a probability of about 0.66. That's because there were only 6 values in this bin, and so two of them were not tagged as smoky, maybe because the visibility was greater than 6 miles, and um, that was the issue right there. So we say, okay, like let's suppose it's a smoky day, and maybe for a couple hours visibility is higher than 6 miles. So, but that day is, it's still attenuating light, so we still want to use it. Let's see if hours that neighbor that hour are smoky or not, and then this is the probability whether an hour is tagged smoky or not within 6 hour window. Um, and again, to cut a long story short, we see that if our above our or the bin between 40 to 45 microgram per meter cube has more than 80% of probability of being tagged as smoky or have a neighbor that is smoky. So we just went with this 40 microgram per meter cube concentration. And so, like to sum it, select today, is there smoke reported between 9 to 4? If it is, yes, then the day is smoky and that would be used in our models. If no, then check PM 2.5 concentration. If it is more than 40, then yes, the day is smoky, otherwise it's not. So that's kind of a novel technique that we have come up with, which we have not seen in the literature for solar PV impact relation with smoke before. Then we also need ideal days to compare with smoky days, and we just make sure that so you can kind of understand like, hey, yesterday it was sunny and there was no smoke and there were no clouds. So like we produced, let's say, 100 kilowatt hour of solar PV energy. Today is smoky. How do we compare with the previous day? And so we find ideal days using this methodology. We try to find 3 ideal days for each month. However, there are some days where, like for example, in June, where the precipitation is highest in Calgary, so you just cannot find good enough days with smooth curves. So you just use days from May or July, and you can see that you have generally higher PV production in May, June, and July, which tapers off towards October. One thing to be cognizant, this is a time series plot, and you can, the dark blue is the actual PV output on a certain day. The dotted one is the ideal output. You can see the ideal output can be a little lower compared to actual production on this day. It's specifically because there is a huge difference in temperature. And so you need to control for other meteorological variables to make sure that the model it works fine. So we also checked for Edmonton. There was an issue where modules started to fail because this is a very old system and it's more than 10 years old and was not maintained. And so we just picked the closest ideal day to each smoky interval. And so made sure that the modules that are not working on an ideal day were the same modules that were not working on the smoky day. So this is a basic formulation, and you need a model which gets some inputs, create an output. We would be using single feature linear regression using PM 2.5 and estimating. So our output variable basically is the ratio of energy produced on a smoky day versus an ideal day or hour. We also have multiple, we also have models that use multiple inputs, which are PM 2.5, temperature, humidity, wind speed, and cloud cover. And the difference is calculated as variable value on a smoky period minus that during an ideal period. So for a single feature regression, you pretty much see no impact of PM 2.5 on smoke. Why is that? That's because there are clouds which also account for like these days right here when PM 2.5 is low, but PV ratio is also low. So we removed the days without clouds. So if a day had on average more than 2 octas, between 9 to 4, that day was removed. You can see a more pronounced, more clear trend. The R squared score is higher. The absolute error, average absolute error is about 7%. But if you're removing the clouds, then remember you cannot use this model in all sorts of scenarios. On most days, you have some sort of clouds. And so, although previous studies have used these, I like cloudless days, but we want a more broader model. And so we really need to account for clouds and other things. But before that, all right, let's go. We also tried the hourly analysis without clouds, but you still see there are a significant number of hours down here. And so we investigated those closely. And what happens is that even though this hour is reported not to have any clouds, but there are neighboring hours which have a lot of clouds. And remember, there is a spatial mismatch between our weather station and our solar PV site. And therefore, the actual cloud coverage at the site may be a little different from the weather station. And so what we did is to remove all the days which had cloud cover more than 6 octaves during any hour. And all of a sudden you see that, hey, this trend looks nice. There still are days which probably should not be there, but then there it is much better compared to what we had before. And because there's a spatial mismatch between our sites, this is to be expected. Now, this was a linear model using only one feature, and we want to adjust for temperature, and we also want this model to include the impact of clouds. So we use other features: temperature, humidity, cloud cover, wind speed. This shows, so basically this plot shows actual versus predicted solar PV. So basically, let's say that this point had an actual PV ratio of around 1.5, 0.15, and this is exactly what the model predicted. So this point is right on track. But let's say this point right here, the actual PV ratio was about 0.55, but the model predicted somewhere close to zero point 0.9. So this point is not well predicted by this model. And so the model performs better than the multiple linear regression model is performing better than the single linear regression model, because, especially because now we also have the cloud data right here. And when we had the cloud data in the single linear regression model, it was all over the place. The R square was pretty non-existent. So it is nice, but it's not perfect. Hey. So we also try this at an hourly scale. The R square is worse, but still better than whatever we saw at the single feature linear model. So what seems to us is that the model is not capturing any nonlinear impacts that may be present. Because remember, we've been discussing only the linear models up until now. So we try a random forest regression model, which is a nonlinear model, which works well on tabulated data. And boom, all of a sudden you see this test R square shoot up to 0.76. And so, of course, there are some nonlinear linearities in how the features work, and so on. And so, using nonlinear model helps in capturing that. These are something called the partial dependence plots and the feature importance. So machine learning models can be less interpretable, so you need different techniques to make sense of how they're working. In any case, this partial dependence plot shows that as PM 2.5 increases, then the solar PV ratio decreases. That's the case for all variables except for temperature. Importance-wise, cloud cover was the most important feature that reduced the training error of the random forest model, whereas wind speed was the least influential feature. We extend this approach to hourly analysis and see that the model is performing better compared to any of the hourly models that we had before. It's not perfect, of course. There are spatial mismatches between our measuring stations and our solar PV sites, and but it's doing a pretty decent job compared to the linear models. These are the partial dependence plots for this scenario, which are pretty much similar. And to sum up until now, we tried three different models and we see random forest performs the best. We also discussed AQHI and AOD, and we want to see how they perform. So in comparison, AQHI is reasonable on cloudless days, but it is not as good as PM 2.5. Um, and then AOD, however, is excellent. It shows a very high R squared of 0.842 on days without clouds. And so if you're doing retrospective analysis, AOD is certainly what you want to use. However, because it's not accessible in real time, as PM 2.5 is, then we would recommend using PM 2.5 as proxy for wildfire smoke. So this is the summary, and we still have 7-ish minutes, and we are done. So I'll leave it open at this point, and I'll invite any questions.
Um, Thank you so much, Irtaza, for your informative presentation. For the audience, please go ahead and feel free to ask your question uh, if you may have.
Yeah, thank you, Irtaza. I think this was a good strategy of talking for 55 minutes, so people don't have a lot of time for asking and criticizing.
I mean,
Yeah.
people can feel free to email me. It's just I wrote a
No, no, good
script.
job. Yeah,
Thought it
good
would
job.
be 45 minutes, but I went
I think we still
over.
have a few minutes for questions. Yeah, thank you. Good job, Irtaza.
Yes, we have 6 minutes for question. Ali Reza, please go ahead. You are muted. We cannot hear you. You are muted.
My bad. You can hear me now, right?
Yes.
Yeah. Thank you, Irtaza, for the great presentation. I have, a few questions. Just I'll try to just ask the most important ones. You mentioned that you have used PM 2.5 from Environment Canada climate change, and I saw that your study period it was till 2025. But as far as I know, the Environment Canada data will, we only have 2023 hourly data available now, and the 2024 data will be available end of April, I believe. I was just, curious where you were able to, to obtain the data for PM2.5.
Yes, no, that's a great question. So let me see. So it is available via ECCC, but there's also a dashboard of Alberta government that provides it. It does not go through one final quality check with ECCC, but I've analyzed some of their historical data and it is pretty consistent. So Alberta government and ECCC report pretty much the same values.
Mhm.
And it's coming from the same station
Yeah,
basically.
yeah, got it. Thank you. And could you please open slide 11?
Okay. Yeah.
Yeah, you talk about ideal day PV. I was curious what approach you have used, to calculate the ideal. Is it something like named capacity or different approach you have used to calculate the ideal output?
No, that's another great question. I'm sorry I couldn't go through this flow chart in detail, but the ideal day for selecting ideal days, I would select that day, make sure it was not smoky, make sure there were no clouds, made sure that it was producing high PV output. Then I checked if the curve was smooth, symmetric, and high production. And then I ranked all the days. And then I selected top 3 days for each month. And then I manually kind of reviewed and saw that if there were days like this, then I removed those. And so, yeah, that's how I would assign the ideal days.
Okay, great approach. Thank you. And the last question that I had, you have used some thresholds specifically for tagging the smoky days. You use 40, I think 40 or 48 something as a
40.
threshold for PM2.5. I was wondering, how did you find that specific value? Why not 41? Why not 39?
No, that's again a great question. And again, I skimmed over this flow chart right here. As I showed before, there were these bins of PM 2.5 concentration. Like now, you can ask like why 40 to 45 and why not 40 to 50? That's a valid question, but that's just somewhere I started. And then what we did is uh, I saw the satellite images for all the days that were not tagged as smoky. Like if a day is tagged as smoky in observations, then it's smoky. That's done. But if it is not tagged as smoky and PM 2.5 is high, then I manually checked all the satellite images, and you can see this is a clear day, this is a cloudy day, there's a little bit of smoke here, there's a little bit of smoke around Calgary here. What I found is for days when PM 2.5 concentration was more than 45, then 85% of those days I confirmed as smoky. If it was between 40 to 45, then 90% of those days were smoky. However, if it was between 35 and 40, then I could only confirm that 70% of those days were smoky. And this reduced as you go further down. So I thought like you want to include smoky days, but you do not want to include false smoky days when maybe PM 2.5 is high because of other pollutants. So that's why I draw a line here.
Oh, okay. Yeah, thank you. Yeah, I have more questions, but to discuss later in person. Yeah, thank you.
Okay, sure.
Thank you so much, Irtaza. And if there is not any more question by audiences, I don't see any more question here. Yeah, we can conclude the meeting here. Thank you so much. And as a quick note, the admin team of Wired seminar series are going to send out an email to all members and ask regarding the availability of everyone's for doing the presentation and Wired Wednesdays series. We would much appreciate if you respond to this email and let us know your availability for doing the presentation. I believe this email will be sent out today or tomorrow. Thank you so much and have a great one, everyone. Thank you so much.
Thank you.
Thank you, everyone.
Thanks, everyone.
Thank you.
Thank you, everyone.